me check if this is right. So if I take del of this quantity, still I am not writing, so it is del u minus ds minus s dt. Du is dds minus pdv minus dds minus s dt. dds cancels out. I get completely a minus sign, and this is minus pdv minus s dt. No, I get a function of t and v. My target is to get a function of s and p. So what should I take here?
PV.
Okay. Let's try. It seems that PV will be the right, but it should be a plus PV, I think. So du plus pdv plus vdv, and du is dds minus pdv plus pdv minus vdv. This cancels out. dds plus pdv. No, yes, right. You got s and p. Yeah. So this quantity is known as enthalpy. Something like a total energy, right? So now my target is write down another quantity. So this is my first equation that I have got. Second equation that I've got. There is a funny incident regarding that. So since we are calculating this, once in an interview for job, some of our friend in Central University of Tamil Nadu was appearing for a faculty position interview, and he was asked that tell these quantities. He told that I don't remember. Then they told her, how can you not remember these things? How can you teach these things? Well, I know legenda transformation. I can calculate everything. So they were quite surprised. So yeah. So similarly, it should happen to you also, that if you know the legenda transformation, you can calculate everything. Don't remember these quantities. So suppose my target is S and P I have done. Now my job is to calculate S and P is done. T and B. What should be T and V? Some function, I don't know. U minus or plus. What? Somebody opened the mic but didn't say anything. It seems that we will be the right, but it should be a plus.
U minus TS.
So yeah. So can you tell me how did you get this thing, U minus TS? I hope you are not remembering these things.
I calculated.
You calculated, right? So which one is U and which one is, so according to this system, which one is U and which one is X? T and X is S.
Yeah.
So T is the U, right? And X is S. Yeah. Thank you. So this will be U minus ds. Then this quantity is known as F, Helmholtz free energy. So that was enthalpy, not to be mixed with it. So let me check it. If I am right, du minus tds What about others? Others are also following, right?
Yes, sir.
Yes.
Yes, sir.
So du is TDS minus PTV. It's TDS. So TDS cancels out. Minus PTV minus ST. Fine. What should be my fourth quantity? So what I am left with? T. So SP is done. S is done. VT is done. I am left with PT, right? So now tell me PT. From this equation you cannot go to PT. For PT you have to go from this equation. Yes. So TT, PT. This equation or this equation, whatever. And yeah, so tell me what should be H minus ST. ST. Okay, let me try. TH minus TTS minus STT. And TH is TTS plus PDP minus TTS. So this is PDP. This quantity is known as Gibbs free energy. Okay. So let me chalk down the four quantities that we have just derived. Write down these things one by one. So first quantity was du is TTS minus PdV. So du is TTS minus PdV. Second quantity was dH equal to TTS plus PdP. dH equal to TTS plus PdP. Then dF, then dG, and dF was minus PdV minus SDT. Minus PdV minus SDT. And this is PdP. So these are the equations that yesterday we had written. And now you can derive any equation from any equation. So as I have told that they are called potential because reason one, their dimension are the dimension of energy, and you can calculate any derivative, any quantity by taking derivative with respect to them in terms of energy. Yes. Now we are going to solve another thing which is known as the Maxwell equations. So these equations comes from a theorem, and the theorem is quite easy to understand, that if you have a function z which is a function of x and y, then your dz is dz dx y dx plus dz dy x dy. Now, if I write this thing m and n, so there is no, you don't need to take notes. These are all I am following Dittman-Zimensky last chapter, 10th chapter. So you can find everything there, or I can circulate in the PDF, whatever you want. So very fine, and this is very easy to derive that dm dy is nothing but del square z del x del y, and similarly del z del y del x is dn dx, and this is also del square z dx. So naturally these two things are same when the derivatives are commutable. Sometimes the derivatives are not commutable and these kind of equations might not hold, right? If the derivatives are commutable, so I mean if you take derivatives with respect to y first, or if you take the derivative with respect to x first, that doesn't matter. In case of the polynomial function, it always doesn't matter. So you can write this kind of things, and in this kind of cases, in most thermodynamics cases, you will find that this will hold true, and in this kind of cases, what you are expected to, what you will get is very simple. Your dm dy is dm dx. So the idea is, if you have a dz which is a function of m dx plus n dy, which can be written as m dx plus n dy, then it simply follows to this. Okay, this theorem is fine with everyone, right? School level mathematics, fine? Yes, sir. Yes.
Yes.
Yes, sir.
Okay. So you need to apply this thing. You need to apply this thing to these 4 equations and tell me one by one. So first with first I am going with du equal to dts minus pdv. What will be the Maxwell first relation if I follow this part thing? First I am going with du. Anyone? dts minus pdv. What will be the Maxwell first relation if I follow this part?
Del T by del V
Del t by del v
is equal to minus del T by del S.
Okay. Minus del
T by
del v. Del t by del v.
minus del T by del S.
Both of the things cannot be t, right? One can be t, one can be p. Which one is t, which one is p?
Del P by del S.
Both of the things cannot be. Okay. Right? One can be t, one can be p. Which one is t, which one is p? And which one will be constant? Here s, and here obviously s. Right? Let me check if it is fine. M. So I write this as m, this as x, this as n, this as y. So del m del y. So del m del y is dv, and nx is ds. Minus sign is absorbed in it. Fine. So then this was number 1. what was our second relation? DH equal to TDS plus BDP. DH equal to TDS plus BDP. Tell me the Maxwell equation. Someone else, not just Raj.
Del T by del P.
Del T
with
by
constant
del
S.
T equals to by del S.
Equals to del.
Del B
B
by
by?
del S.
What will be the constant thing here?
P.
And what will be the constant thing here?
S.
What will be the constant thing here? Third equation, df equal to minus pdv minus sdt. df equal to minus pdv minus sdt. Someone else?
Del P by del T equal to del S by del V.
Del s by del. Someone else? What will be the constant this side?
V.
And this side?
T.
Good. What will be the constant this side? Del G is PDP minus SDT. Okay, someone else?
Del V by del T with del by del co equals to minus del S by del P with constant.
Okay, so the four equations now we have with us, right? So these are my Maxwell's equations. We will use this quantity in our next calculations. So if you see the tutorial thing, where is the tutorial files? Calculations. So if you see, there is one question, 1, 2, 3. So like this. The heat capacity Cv at constant volume of a metal as a function of temperature is alpha T beta T cube. This is cube. Where alpha, beta and constant, the temperature dependence of the entropy at constant volume is what you have to calculate. So temperature dependence of the entropy, this is something they want us to calculate. So if we go to our calculations today, what we have to calculate is ds dt, and as they have already told it is a metal, so there is no other question, but still they have also written it constant volume, so you can understand that you have to calculate del s del t at v, right, from cv, from the expression of cv. So, using these equations you can calculate that, I hope. Okay, so someone's background noise is here. Okay, thank you. Someone's background noise is here. Okay, so so far we have calculated this thing. Now we have to do a few more things which are important. One thing that is now we have the intuition should be clear to you is that the internal energy for the ideal gas, right? So so the internal energy, again I am starting with U d U equal to dTs minus PTV. So suppose I have a gas volume, right? Internal energy, again I am starting with U. If I have an ideal gas inside it and I increase the volume of the box without transferring heat or without doing anything, what should happen? Should the internal energy of the gas increase or decrease? I am not providing any heat. I am just expanding the volume. What should happen? Should the internal energy of the gas increase or decrease? Anybody? Any intuitive idea? That my internal energy of
It may decrease.
okay, so let me check that if the internal energy of a system is actually for ideal gas can depend on volume or cannot depend on volume. So du dv is dTs dv minus p, right? If I keep my temperature constant, if I supply, I have to supply energy. If I keep my temperature constant, yeah. If I do not, supply the energy, the temperature will not be constant. So it will be an isothermal process, not an adiabatic process. So my temperature is constant. I am supplying heat Q and I am expanding the volume. What will be the energy? Yes, anyone? Obhishekta. Hello.
Yes, sir.
So I am the thing is that I am supplying energy. I am maintaining the temperature constant, and similarly I am increasing the volume. What should be my internal energy? Should it be constant or should it decrease or should it increase? Yes. Anyone else?
Should it decrease?
See, I am supplying energy. I am increasing volume. I am keeping my temperature constant. Should my internal energy increase or decrease for an ideal gas?
Maybe no change.
Yes. Why?
Because the temperature is constant here.
Constant. Yes.
So-
Yes. And internal energy is actually function of temperature only for ideal gas, right?
Yes.
Yes. So everybody has gone through the thermal, that kinetic theory of gases, right? So if you have n particles and if they have m degrees of freedom, then every degrees of freedom will have half kT energy, right? And if you have n number of particles, then the total is n mkt, right? So the temperature is the only thing that gives your U, it increases or decreases your U, right? So volume and the pressure are not the things for an ideal gas. Again, for an ideal gas, your du is the only function of temperature that you typically see from a kinetic theory of gases, right? This is a microscopic description. Kinetic theory of gases. You get this U is mm half kT, right? This is a microscopic description. In macroscopic description, what is the equivalent thing that you have? Is the ideal gas equation, PV nRT. So if I put this thing here, just check ds dvt from the Maxwell equation we have already calculated somewhere. Where is ds dv? Yes, so this is ds dvt is dp dtv, right? So d dp dt v minus p. Ideal gas equation is pv equal to nRT, right? So dp dt v is n r by v, right? So this is, so I follow from this thing is that t n r divided by v minus p, and minus p is again nRT v. So this cancels out and it's 0. The idea is, so this is, so what you have just seen? You have just seen that internal energy, which is dU, is independent of the volume in case of constant temperature, and that followed from the ideal gas equation, which is a macroscopic definition, macroscopic physics. I haven't considered anything about the microscopic thing. Whereas the microscopic theory, which is the kinetic theory of gases, that tells me that this is N m kT by 2. So this description and this description, although this is the microscopic description, this is the macroscopic description, these two descriptions are equivalent. So from microscopic description, you can easily understand that, okay, this U should not depend on that, right? But from the macroscopic description, which is the ideal gas equation, and you have no idea why, you have no idea about the internal physics, but still you can come up to this conclusion that U is only a function of temperature and independent of the volume. Is it fine?
Yes, sir.
Yes.
Yes, sir.
So okay, so now 2 or 3 small, this kind of couple of things, and that will be all for our today's class. So now we will derive some TDS equation. TDS equations are quite important things in thermodynamics, and they are quite easy to calculate also. So as we have told you that we have S, V, T, P, 4 variables. All these 4 variables can be written as a function of each other. So I can write S as a function of T and V. Now you might now ask me, then if I can write this thing as a function of this, then obviously my ds will be del s del t dt with v constant plus del s del v t dv. Can I write s as a, can I consider s as a potential or not? If somebody tells me that, okay, I can write entropy also in this kind of form, the way you have written your du is TDS minus PdV, I can write my entropy also in this kind of form. But can I say S as a potential or not? I cannot say S as a potential because it do not satisfy the criteria that I can calculate everything from its derivative, right? So this is not a potential. This should not be considered as a thermodynamic potential. And otherwise, that four thermodynamic potentials that I have already earlier told, they have this quality that you can calculate anything from that. Okay, so if I can write this thing as this way, then the next procedure is writing the TdS equation, where T ds dt v dt plus T ds dv dv. See, if my volume is constant, this thing we know that this is the transferred heat, right? And if my volume is constant, this term goes to 0. So this part is nothing but dq dt with constant volume is T ds dt. So transfer of heat, derivative of transferred heat in terms of temperature for constant volume. What this quantity is known? Anyone? Yes. Transferred heat with respect to temperature when volume is constant. What this quantity is known? Yes? Yes, Kaunte?
Entropy.
Entropy is here. This is dq dt v, right? So I have a system. I am heating it up. From T to T plus delta T, and I am giving some volume, some heat, which is delta Q, right? Then the amount of heat given divided by the amount of temperature raised when the volume is constant. What is this? Heat capacity. Yes, Vivek, your voice is breaking a little bit. Heat capacity at constant volume. Exactly. Yes, thank you. So this is heat capacity as constant volume, CV, right? Similarly, if I done the same kind of thing by keeping pressure equals to constant, then it would have been Cp, right? So what did I get? So just already, you have already derived this equation, right? Just look at this thing, right? So you have to just use this thing for your assignment that I was just showing. So what is it telling? That your Cv is alpha T beta T cube, where alpha beta is constant. The temperature dependence of the entropy at constant volume is given by what? Right? So your Cv is alpha T plus beta T cube. Sorry, T cube. Right? You use it and you calculate S as a function of T. That's all you have to calculate. So if you do not remember these equations, now when you face these kind of problems in the exam, you will forget that what Cv is T ds dt. It is hard to remember. Just remember the concept of Cv. That remember the concept of specific heat. What is specific heat? Concept of specific heat is that you are heating up some material and the amount of heat is delta Q. amount of increase in temperature is delta T, then del Q del T at constant V is the specific heat, right? CV. Very good. If you now you remember the very fundamental equation that you have undergone in your life, that is du equal to TdS minus PdV. So it will take you couple of minutes just to arrive at this equation, right? Your TdS is equal to del Q, and you need just one Maxwell equation. So one Maxwell equation, this equation I think you will never forget in your life because everywhere you will encounter. So one Maxwell equation, one first law of thermodynamics, and you can easily come up to this quantity that dq dtv is nothing but dt dst is equal to cv. Does anybody has any question? Okay, so this thing is okay, fine. So let me. Yes.
Hello.
Yes.
So can you explain the reason why we cannot write entropy as a function of T and V?
Entropy cannot be a function of T and V.
Yes. At the top of this page, you said that we cannot
No.
write.
Yeah, entropy is a function of T and V, as I have told. Entropy can always be written as a function of T and V. But since it is written in this kind of form, do not take entropy as a thermodynamic potential. Never consider entropy as a thermodynamic potential. Because thermodynamic potentials are those quantities, by taking derivative of those quantity, you can calculate all other quantities. Entropy is not like that.
Oh,
okay.
okay.
Entropy can always be written as a function of T and V. That's why I have written. So I have taken the entropy function of T and V. That's why I can do this expansion. I just multiply T in the both side, and I got this equation. Fine.
Yes.
So you can consider it, but do not consider it since it can be written. So all the things which can be written as a function of each other should not be considered as thermodynamic potential. That was my point. So yes, so you got the TdS equal to, this thing is CV that you have calculated. So TdS equal to CV dt plus T. Okay, so another quantity is ds dv at T. For the volume constant case, we had made this thing 0. But what is ds dv at T? Again, go to the Maxwell equation. ds dv at T, where ds dv at T, this one, third one Maxwell equation. So it is dp dtv, right? So dp dt v dv. Okay. So this one is one TdS equation that you will require at many places. I am already running out of my time. Very quickly, the other TdS equation that you will need, that I can just give you a try, so you can calculate or do this thing so that this becomes a note. So S, as I have told, you can take it as a function of V and T. S always can be written as a function of other two. So ds is equal to del S del P dT plus ds dt dt. Again you do the TdS ds dt p dt. plus T ds dp dp. You go to the Maxwell equation and okay, for dp equal to 0, this is delta q. So this is delta q delta t at constant p is t ds sorry t ds dt as p, right? And this thing is cp, because at constant pressure this signifies the rate of heat that you have, amount of heat that you have given. So your Maxwell equation, you need one Maxwell equation here, ds dpt, ds dpt. Let's find out ds dpt, ds dpt, ds dp. No, here fourth Maxwell equation. The ds dpt is minus dv dtp. So this thing is minus dv dtp. So you have TDS equal to CP dt minus dv dt p dt. Okay, so for today I end my lecture with these two TDS equation. Next day I will show that how these two TDS equations are used in thermodynamics to calculate the quantities, and I will discuss the thermodynamic stability conditions and others. After that, from the next week, we will move to the statistical mechanics. So do anyone have any question now? Hello?
Hello, sir.
Yeah.
So for ideal gas, as you said that
Yes.
internal energy depends on only on temperature.
Yes.
So for if we consider the case of real gas, then on
Yes.
what factor does the internal energy depends?
Yes. So the very good example would be van der Waals equation. So what you can calculate is very easily, just try to do that. A very simple calculation. Here you have taken this PV equal to nRT, right? So you know the van der Waals equation of state?
Yeah.
Yeah. So van der Waals equation is P minus something, V minus something, and that becomes nRT. So you use that van der Waals equation of state, and then you show what will be this du dvt, right? So in real gas, you will find that the internal energy is not actually the function of temperature only, but it depends on the volume also. So two gases which are kept in large volume and small volume, but in same temperature, they have different internal energy in the real gases. Just using the van der Waals equation here, you can prove that.
Okay, sir. Thank you.
Okay, anyone else? So fine, tomorrow please do those problems, and tomorrow we will just try to solve those problems. And before, 3:15 is the starting time of the class. It will be fine if you can send the scanned photocopy of your solutions. And so in front of you, I will open those things, and you can explain to me, and I will see that what you have done, and what we have till done, or what you have studied in the DSC, if that is sufficient to solve those problems. If you need something, I can tell you. So, fine. Is it okay?
Okay.
Okay. Fine. Bye. See you tomorrow.
Bye, sir.
Bye, sir.